Today we are diving into a Rust app that turns your file system into a holographic Rolodex. Instead of showing files as one more flat list, this app arranges folders and files like glowing spatial cards in a curved deck. You can browse directories, open files, move through history, sort, filter, create folders, rename items, delete entries, and restyle the interface. But the whole thing feels less like a normal file explorer and more like operating some retro-futurist archive machine. The app starts in main.rs, creates the window and renderer, builds the app, and immediately loads the current directory so the interface comes alive right away. And that is why I think this project is interesting. A file browser is one of the most ordinary tools on a computer, but this app treats it like something worth reimagining. It is the kind of project that makes you feel like a genius right up until you remember it is touching the real file system, which means the code underneath actually has to be good. So in this video, I want to break down what the app does, how the Rust architecture works, and why this holographic Rolodex idea is more than just a cool visual. And along the way, I also want to explain the Rust concepts that show up naturally in the code: modules, structs, enums, pattern matching, ownership, borrowing, option, result, state transitions, and why explicit data models make complex software easier to understand. You can see those ideas clearly in the app controller: the state model, the style panel logic, the card model, and the scene rebuild path. By the end, you should understand not just what the app does, but how the code is structured and why Rust is such a strong fit for building something practical with real visual identity. Like and subscribe for more videos on coding and useful tech content. Before opening specific files, I want to start with the shape of the project because structure tells you a lot about how to read Rust code. This project is split into modules like app, domain, file system, platform, render, scene, and user interface, and then it's all pulled together from main.rs. That matters because modules are how Rust keeps responsibilities from drifting all over the place. You would not throw tools, receipts, spark plugs, and fishing gear into one box and expect to find anything quickly. Modules do that kind of organizational work for the code. They let the project say this part handles app behavior, this part handles scene layout, this part handles user interface helpers, and this part deals with file system work. That gives the app a clean overall flow. Input comes in, input becomes an action, the app interprets the action, state changes or a command is dispatched, file system work happens off the main interaction path, responses come back, the visible card archive is rebuilt from the latest truth, the render draws the current state, and that is the whole pipeline. Now once you see that, the app becomes much easier to reason about. Now let's go to main.rs because that is where the app starts moving. The startup path is straightforward. Logging is initialized, the event loop is created, the main window is built, the renderer is constructed, the current working directory becomes the start path, the app is created, the input mapper is created, an initial load directory command is dispatched, and the first redraw is requested. Now that initial load is important. It means the app is not launching into an empty shell. It immediately asks for a real directory snapshot so the UI has something meaningful to show right away. Then we get to the event loop. The app uses control flow poll, which means it wants to stay actively responsive. It matches on incoming events. If the window is closed, it exits. If the window is resized, the render resizes. If a redraw is requested, the app ticks and the renderer renders. Otherwise, regular window events are mapped into higher level actions. Those actions are applied, and the app ticks again. Then about to wait, requests, redraws, at a smooth cadence. This is a good place to explain match. Rust's match is one of the language's most important features. It is how the code handles variance explicitly. Instead of vaguely checking what something might be, the code says, if it is this event, do this. If it is that event, do that. It forces a kind of honesty into control flow. This is also a good place to mention results. The run function returns anyhow results, which means startup can fail in a structured way. And that is how real Rust code tends to think. It does not pretend failure is impossible. One of the first things I like about this app is that raw input is not wired directly into behavior all over the project. Instead, the app uses actions. You can see that an app apply action, the app reacts to things like move selection left, move selection right. Let me pull this up here. All right, here we go. App apply action. So we got our function apply action. Bam. The app reacts to things like move selection left, move selection right, scroll, open selected, go up, navigate back, navigate forward, start, search, update search, clear mode, set sort, cycle sort, create folder, begin rename, confirm rename, request delete, confirm delete, click at a point, resize the viewport, toggle the style panel, cycle color palettes, hover an index, select an index, activate a favorite, navigate to a path, or do nothing. That is a huge architectural win. Because once the rest of the program speaks and actions, it no longer cares whether that action came from a keyboard key, a mouse event, or some other input source later, like your brain or your eyeballs. It just reacts to meaning. This is also a great example of Rust enums doing useful work. An enum is how Rust represents one value that could be one of several valid variants. Instead of scattering strings like open or delete around the app, the code can use a real typed action model. That is one of the big lessons in Rust. If something has a real set of valid states or commands, encode that in the type system. Now let's move into the app controller, because this is where the behavior of the whole program comes together. The app struct owns two major things. Let me scroll up to the app struct. The application state and the file system service. That tells you exactly what its role is. It is not the renderer. It is not the card layout engine. It is not the file system implementation. It is the coordinator. And the three key methods reflect that role very cleanly. Dispatch takes a high-level app command and turns it into a file system request. Tick drains any pending file system responses and then refreshes the visible scene. Apply action takes semantic user intent and turns it into actual app behavior. And this is also a good place to explain mute self. And this little right here, ampersand and mute self. When you see that ampersand mute self, MUT self, and a Rust method signature, it means the method needs mutable access because it is going to change the value. Rust puts that decision right in the method signature. The code tells you up front whether it is reading state or mutating it. Looking through apply action, you can see the whole behavior map of the app. Move left and right, update the selection. Scroll also moves through the deck. Open selected either navigates into a folder or opens a file using the operating system default app. Go up computes the parent path. Back and forward navigate history. Starting search changes the user interface mode. Updating search changes the filter query and clamp selection. Set sort updates the active sort key. Cycle sort rotates through sort modes. Create folder dispatches a folder creation command. Rename enters rename mode and later dispatches a rename command. Delete goes through a confirmation flow. Clicks get routed through style panel, hit testing. Theme actions cycle the live visual palettes. And that is one reason this project is so teachable. The behavior is centralized enough that you can actually follow it. And it's mostly written in plain English, so. Now let's open App State, because this is where the shape of the software becomes really visible. App State contains navigation, directory state, selection, sort state, filter state, scene state, user interface state, visual theme state, pending operations, and notifications. That is almost the whole product in one data structure. Navigation tells you where the user is and where they have been. Directory state tells you what snapshot is loaded, whether the app is currently loading, and whether there was an error. Selection tells you what card is focused. Sort and filter describe how the visible deck is transformed. Scene state stores visible cards, deck capacity, previous positions for motion continuity, and reduced motion preference. Now the user interface state stores mode, pending delete path, breadcrumbs, inspector text, and viewport size. Visual theme stores palette state. Pending operations and notifications store what the system is doing and what it wants the user to know. And this is one of the strongest Rust lessons in the entire code base. The program becomes easier to understand when the important ideas are explicit in the data model. This is also the right place to explain option. The snapshot is optional because it may not exist yet. The pending delete path is optional because there may or may not be something queued for deletion. Hovered card is optional because the user may or may not be hovering over a card. In Rust, option T means exactly that. Maybe there is a value, maybe there is not. The language wants that uncertainty to be visible instead of hidden. Now, the user interface mode system is another good example of explicit modeling. The app uses a UI mode enum with normal, search, rename, and delete confirm. Now let's find this user in mode. Now that is much better than a tangle of booleans that can contradict each other. Instead, the code can ask one clean question. What mode is the interface in right now? This is how good Rust code often works. Instead of leaving states implied, it models them directly. Selection is intentionally small and focused. The state tracks a selected index and an optional hovered index. The app moves left, moves right, resets selection, and clamps it when the visible set changes. That clamp step matters because once filtering or sorting changes the visible entries, the current selection might no longer be valid. Sorting and filtering are treated as first-class transformations of the current snapshot. Filtered entries clones the current snapshot entries, filters them using the current query, sorts them using the current sort state, and returns the transform list that drives the visible deck. That distinction matters a lot. The raw directory snapshot is not the same as the current visible archive. The visible archive is a transformed view of the underlying data. And selected entry is careful about mapping selection back to the original snapshot by ID after filtering and sorting. That means selection stays tied to the real entry, not just a temporary place in a reordered list. The theme system is another nice piece of architecture. The visual theme stores whether the style panel is open and which palette indices are active for text, outlines, and background boxes. There are methods for cycling those palettes, methods for turning them into RGB values, and methods for returning human readable names. That is a good example of behavior living close to the data it belongs to. The overlay layer also matters. It builds lines like path spine, mode, filter beam, deck count, and latest notification. So even though the main attraction is the glowing spatial archive, the app still gives the user practical context. And the style panel hit testing is nicely explicit too. The app defines a style panel hit enum with variants like none, toggle panel, cycle text, cycle outline, and cycle background boxes, plus helpers that define rectangles for the button, the panel, and its rows. That is another small example of enums and helper functions keeping UI logic clean and inspectable. Now we get to one of the most important design choices in the whole project. File system work is kept away from the hot interaction loop. From the app controller, we can see high-level commands turning into file system requests like load directory, create folder, rename, and delete, and later responses being received back in tick. That means the app is not directly reading directories or deleting files in the middle of input handling. Instead, it is using a service boundary and message passing. That is where Rust's concurrency story becomes relevant. A very common Rust pattern is to isolate side effect heavy work behind requests and responses, often using threads and channels. Even from this code alone, you can already see the benefit. The app keeps UI behavior and disk operations separated. And that matters in a real file browser. Once software touches the file system, we want good boundaries. Inside dispatch, directory load sets the loading flag and sends a request. Create, rename, and delete push a pending operation label and send the corresponding request. Then in tick, the app drains all available responses and handles them before rebuilding the scene. Handle file system response is especially useful to study. Successful directory loads update the current path, store the new snapshot, reset selection, and clear errors. Failed directory loads push an error into state and notifications. Successful operations remove a pending op, push a notification, and reload the current directory so the visible world matches the actual file system. Failed operations push error notifications. That automatic reload is a very good design choice. Instead of trying to patch the UI by hand after every mutation, the app refreshes from the source of truth. I'm not addicted to generating code. I can stop anytime. But this is also the point where the joke has to step aside for a second, because once the app is creating, renaming, and deleting real things, the architecture underneath matters more than the glow. That is why this clean separation between action handling, command dispatch, file system work, and scene rebuild is so important. Now let's move into the scene layer, because this is where the app earns the holographic Rolodex feeling. And let's move into the scene. Alright. Card. Okay. A scene card is not just a label and a position. It stores an ID, label, category, position, rotation, scale, panel, size, opacity, focus weight, hover weight, shape kind, and target position. That is a very good example of data modeling with a struct. Instead of passing a bag of unrelated values around the renderer, the app defines a real type that represents a visual object in the scene. The category field is also important because the app distinguishes folders, files, executables, symlinks, and other entry types. That means the scene layer is not just decorative, it is carrying semantics. Now we get to the visual heart of the app, curved deck layout. Curved deck layout. This function takes the entries, selected index, max visible count, active query, and hovered index, and returns a deck of scene card values arranged along a curved arc. If there are no entries, it returns an empty vector. Otherwise, it takes a window around the selected entry and lays that visible slice out around the code explicitly describes, or what the code explicitly describes as a Rolodex arc around a hidden spindle. Now that is the key idea. The centered item gets the strongest focus. Items farther away from the center shift in X, Y, and Z. They rotate around the y-axis to stay readable. Their scale falls off. Their opacity falls off. Folders, files, executables, and symlinks get different visual treatment. And if there's an active search query, non-matching entries get visually de-emphasized by reducing opacity. That is why this works as a holographic Rolodex instead of just feeling like a normal file list with some 3D styling layered on top. The data is genuinely being arranged into a spatial archive. The visible deck is rebuilt through rebuild scene deck, which takes the current visible entries, selection, hover state, max visible count, search query, previous positions map, and reduced motion flag. It calls curved deck layout, then applies temporal positions, then eases cards towards their target positions. This is a really nice piece of the design. Instead of cards teleporting into their new places every time state changes, the app preserves continuity. Apply temporal positions looks up prior positions by card ID and interpolates from old position to target. If the card did not exist before, it starts slightly forward in Z space. Then ease cards lerps further towards the target. This is also a good place to explain borrowing again in practical terms. The previous position map is passed in by reference. That means the scene builder gets access to it without taking ownership of it. Borrowing is one of the core ideas in Rust. It lets one part of the program use data owned by another part without duplicating everything or losing track of who is responsible for it. And motion continuity matters a lot in a spatial interface. The user should feel like the archive is turning, not like the whole world is being reassembled from scratch on every interaction. And the camera is doing exactly what it should. The camera struct stores eye, target, up vector, aspect ratio, field of view, and near and far planes. Then it constructs a view projection matrix from those values. This is another good example of a focused struct doing one job well. And the chosen values tell you something about the design. The camera is stable and disciplined. It is not trying to steal attention from the deck. The visual drama comes from the cards and the layout, not from a camera flinging itself around. That is a good decision because a file browser still has to be readable. Now let's trace one interaction all the way through. Suppose I press enter on the selected card. Let's see here. The input layer emits open selected. App apply action receives that action and calls open selected. Open selected gets the selected entry. If it is a directory, the app navigates to that path. If it is a file, it asks the operating system to open it and pushes a success or error notification. If the selected thing is a directory, navigation flows into navigate to, which normalizes the path, checks whether it is actually new, updates navigation history, and dispatches load directory. Then the file system layer responds later. On the next tick, the app handles the response, stores a snapshot, resets selection, refreshes breadcrumbs and inspector text, rebuilds the deck from the current filtered entries, and the renderer draws the new scene. That is the whole design philosophy in one flow. Intent becomes action, action changes state or dispatches work, work comes back as data, the archive is rebuilt from the latest truth, end-to-end example, delete flow. Now let's trace delete. The user requests delete. The app does not immediately delete anything. Instead, it stores the selected path in pending delete and switches UI mode to delete confirm. Then if the user confirms, the app dispatches the actual delete command and returns to normal mode. Then if the user confirms, when that operation succeeds, the app removes the pending operation, pushes a notification, reloads the current directory, and the deleted card disappears because the visible deck was refreshed from fresh file system state. That is exactly the kind of clarity you want around destructive operations. Now, it's all fun and holograms until the app starts doing real file system work. At that point, the joke stops being, look at this glowing archive, and becomes, please do not rename the wrong thing. And that is why the architecture matters. Now, stepping back. Stepping back. This is also a very good Rust learning project. It teaches modules because the project is divided into meaningful areas. It teaches structs because things like app state, scene card, and camera model real concepts directly. It teaches enums because actions, UI modes, style panel hits, and card categories are all represented as finite typed variants. It teaches pattern matching because the event loop and behavior flow are built around matching on those variants. It teaches option because absence is modeled explicitly. It teaches result because failure is real and has to be represented. It teaches borrowing and ownership because the code has to decide what data is owned, what data is borrowed, and what mutation is allowed. It teaches state-driven design because the renderer consumes the current truth instead of building the UI directly from raw events. And it teaches architectural discipline. Rendering stays rendering, state stays state, UI helpers stay helpers, scene generation stays scene generation. So what does this app get especially right? First, the layering is strong. The event loop, controller state, model, theme system, overlay helpers, card model, deck rebuild path, camera, and motion helpers all have distinct roles. Second, the state is explicit enough that you can understand the program by studying the data model. Third, the visual identity is real. The curved deck layout and motion logic generally support the holographic Rolodex concept. Fourth, the app stays practical. It still does the real work of a file browser needs to do. Load, navigate, sort, filter, rename, delete, open, and inform the user. If I were pushing it further, I would look at richer text input for search and rename, more precise card hit testing, live directory watching, and maybe more visual metadata like icons or thumbnails. The current structure looks like it could support that kind of growth. That is the deep dive into the holographic Rolodex file browser in Rust. What I like about this project is that it takes one of the most ordinary jobs in software, browsing files, and treats it like something worth redesigning. Instead of another flat utility window, it turns the file system into a curved archive of glowing cards that you move through like some retro future memory machine. And that is the part that sticks with me. This app is practical. It can load directories, track history, sort and filter entries, rename them, delete them, open them with the operating system, and keep the user informed about what is happening. But it also has a point of view. It does not just work, it feels like something. And I think that matters. Because good software is not only about correctness and performance. Sometimes it is also about giving a familiar task a new atmosphere, a new texture, or a new sense of presence. This project shows that Rust can absolutely do that. It can give you the structure, the safety, and the control to build something disciplined under the hood and visually distinctive on the surface. So if you take anything away from this project, I hope it is this. Even a file browser can have personality. Even a utility can feel cinematic. And even a pile of folders on a disk can be turned into a holographic card archive if the architecture underneath is strong enough to support the illusion. And that is what makes this app memorable. It is not just a Rust project about files, it is a Rust project about giving files a stage. And that's all, folks.